Hello everyone, welcome to my channel. Today we're going to solve another programming problem on spotch.com. It's called prime intervals. Please take a moment to go through the problem. You can also pause the video and attempt to solve it yourself. Otherwise, just continue on and we can try to solve it together. All right, so what do we need to do here? Basically, there are t test cases. And for every test case, we are given two integers, L and U, which are essentially the lower bounds and the upper bounds of an interval. And the bounds lie in this interval. This number is 2 to the power 31 minus 1. And the maximum size of the range is 1 million. And given these two numbers, we need to output all the prime numbers in that interval. So we are given a range between L and U, and they both lie between 2 and 2 to the power 31 minus 1. Which is the maximum size of a signed integer, signed 32-bit integer in C++. And the maximum size of this range is 1 million, or 10 to the power 6. If you happen to look closely at the problem statement, there is a strict memory limit on our program. So we will not be able to initialize any vector, for example, of this size of 1 million. An efficient technique to compute all prime numbers in a given range is known as the Sieve of Eratosthenes technique. And this is what we are going to use to solve our problem today. Right, so how does this work? Let's list down a few numbers. We start from 2 because 1 is not considered a prime. Yeah, let's stop at 25. So how this method works is you start at the beginning. Initially, they're all marked prime, and the first one is chosen. And then we mark all of the multiples of this number as not prime. So the next multiple is 4. So 4 is not prime. 6, 8. So you see we strike out all the even numbers, which we know are not prime. And we start off at the beginning again, and now we have 3. So 3 is a prime. And then we go through the list and strike out all multiples of 3. So 6 is already done, 9, 12 is done, 15, 18 is done, 21, and that's it. Now the next one is 5. We mark it. 5, 10, 15, 20, 25. All right, moving on, 7, 14 and 21. 11. The next multiple of 11 is 22. It's marked. So 11 is done. 13. Of course, the next is 26, which is outside of our range. So all the remaining ones are actually our primes. Okay, so if we are given another range, and then we are also given a list of prime numbers, let's say yeah, these should be enough. We need to compute the prime numbers in this range. Yeah. So what we do is we follow another algorithm, which is a variant of the Sieve of Eratosthenes. It's called the Segmented Sieve of Eratosthenes. So how this goes is, for every prime number in this range, we compute this value low here is basically the lowest number in our range. And then we take the floor of this and multiply it with p. Okay, this gives us our start index. So for p2, we get the start index of 30 by 2, which is 30. And then we start at an index I, which is basically s minus low. In this case, it's 30 minus 30, which is 0. So we start at the 0th index, and we increment I by the prime number. So let's do this for 2. The first one is, of course, 0. So we cross this out. We increment by 2. The even numbers are all gone. All right, so let's start with 3. 3 gives us, again, 30. So our starting would be 0 again, and we increment by 3. So we start at 30, it's already crossed out, 33, 36, and 39. Let's start for 5. That's, again, 30. I is 0. So we start at 30, strike out 35 and 40. And then for 7, we would have 28. And 28 would give us an I of minus 2. And what happens when we get a negative I is that we add p to it. So now we add 7 to it, gives us 5. And that becomes our I. Right? So what's 5? 0, 1, 2, 3, 4, 5. 35 is already striked out. 40 and so on. Let's try 11, 22. Yeah, 22. 22 minus 30 is minus 8. Minus 8 plus 11 would be 3. 0, 1, 2, 3. 33 is done. Plus 11 is 44, so it's outside the range. And 13. 13 would be 26. 26 minus 30 is minus 4. Plus 13 is 9. So I guess it would be 39, which is the first one will be checked out. Yeah, so we are left with our primes in this range, which are 31 and 37. Now you must be wondering what should be the size of this prime number array, right? We had from 2 to 13. What if we have a very short array, which means we only have like 2 prime numbers? Then we would have some numbers which are actually not prime. For example, 35 is misclassified as prime because our initial prime number array was too short, so we could not find out the multiples of 5, for example. So to alleviate this, our starting prime number set should consist of all prime numbers, which could be factors of any number in our query set. If we take a look at the factors of any number, let's say AB is equal to n, we can write n as square root of n times square root of n. So you can see that at any moment, if a is greater than square root of n, this implies that b has to be less than square root of n. So at any moment, one of the factors of n is always less than square root of n. So for any range between L and U, the maximum prime number that we need to have in our initial set should be greater than the square root of U. And since we know that U is bounded by 2 to the power 31 minus 1, this is the maximum prime number that we need to compute. All right, so let's employ what we just discussed in code. I've included a few headers. Let's start with our segmented sieve function, which takes in a vector of our primes. Then it takes in these two numbers which define our range. So our range is closed at low and open at high. So it includes low and does not include high. Right? Then we initialize our vector. We call it segment. This would basically store the Boolean values from low to high for every number. And it'll be true if it's prime and false otherwise. So initially we assign all numbers to be prime. Now let's iterate through our primes array. You can use this range-based for loop. And for the case when the square root of our upper bound is less than p, now we just need to break. And we compute our start variable as we discussed. This is basically the rounded value of low divided by p times p. And if start happens to be less than low, we need to increment it by p. And if start happens to be equal to p, we just start at the next multiple of p. All right. Now all we need to do is to set all the multiples of p in our range. The index would be given by start minus low. It goes to high minus low. It does not include high, so it's less. And we increment the index by p. So all of these numbers are not prime. So now we just need to print out our primes. So if segment I is prime, print it out. So since the first element of segment corresponds to low, our prime is given by high plus low. All right, so we need to compute the upper bound of the maximum prime number that we need to compute. So this is given by, let's call it max num to test. We need to cast this to an unsigned int, as it's the result of a double, which is the square root of the maximum value of n in 32. Yeah, that's our upper bound of the maximum prime number that we need to compute. And this is given by the square root of 2 to the power 31 minus 1, which is essentially this quantity here. So we need to prepare our sieve, the initial prime number sieve. We take this Boolean array of numbers, set all of them true. Then we take a vector of primes. This is where we will filter our primes into, and also reserve some memory for it. All right. So now we employ the original Sieve of Eratosthenes algorithm. Start from 2. Since 2 is the smallest prime that we need. If the number is prime, we can directly add it to our primes array, and we need to set its multiples to not be prime. So let's call it multiple. It starts from 2 times num. It's the size of our array, and we increment multiple by num. Right. Set to not prime. Great. So we have our prime number array now. We are all set to call segmented sieve on our actual test cases. L and U as in the original problem statement, which correspond to our lower and upper bounds. And we run this while loop. I'll show you why in a second. So what we can do here is I can just call segmented sieve with primes L and U. But there is a slight problem here, as we know that the difference U minus L could be a maximum of 1 million, and this would initialize this segment vector to 1 million, which would exceed our memory limits. And that's exactly why we have segmented sieve in the first place. We can call it with a much smaller number, let's say we call it limits, and let's take a limit of 10,000. And what we do here is we take the minimum of U plus 1 and L plus limit, right? So at any moment of time, we are calling segmented sieve on this range, L plus limit. And then what we need to do is we increment L in this while loop. So the next time it will be called on L plus limit is of course open, and L plus twice limit. And so on, it'll keep going until U plus 1. Yeah, this is it actually. We try to run our test case here. I'll show you our test case. And that's our answer. Right, let's try to submit this. Submit solution. We pick CPP 14. Looks all right. And there you have it. So we solved prime intervals today. Thanks for watching, and see you guys in the next one.